Just like how we had defined performance metrics like CPI and execution time for the data paths, we would like to define a metric to measure the performance of a memory subsystem. So the metric that we're going to use is called the average memory access time, or AMAT. So the memory access time is the time that a load or a store instruction takes to retrieve data from memory, wherever it is. It could be in the cache, it could be in the main memory, or it could be in the disk. So for a given load or a store, you can ask the question, how long does it take for me to get the data from the memory hierarchy? Now, if you compute that time for every single load and store instruction in your program, and then you take the average of all that, what you get is average memory access time. So it tells us on an average how long a given load or a store instruction would take. And we would like this latency to be as close as possible to cache's latency. And that would be true if majority of loads and stores are serviced by the cache. So there are several ways in which we could compute average memory access time. One very naive method to do it would be to compute the time for every single load and store, and then you take a simple average. So for example, if you go back to the illustration that we did for a simple cache architecture, we observed that we had 3 misses and 2 hits because we had 5 load instructions. And let's say we make some assumptions about how long the cache would take to access. Let's say it's 1 cycle, which is a fairly realistic assumption. And let's say that main memory would take 15 cycles. Now that's a little bit unrealistic because typically it takes much longer than that, maybe 100 or even 200 cycles. And I'm also going to assume that this time includes the time I'm going to spend in checking whether it's a cache hit or a miss. And keep in mind that I first have to check the cache, and if it is a miss, then I go to the memory. So if you look at the problems, this assumption could be stated in a few different ways, so you have to be a bit careful about how you process this information. Alright, so now I have this information. I could then go and compute the AMAT for this very simple program with 5 load instructions and a cache hierarchy. What I could do is I could say, well, 3 are misses, so each one of them would consume 15 cycles. 2 of them are hits, and each one of them would consume 1 cycle. Add them all up, I would get a number, divide them by 5, then I would get AMAT. Another way to do it would be to use this formula that is given to us here. What it says is AMAT can be computed as the cache latency, which is 1 cycle in our example, times the hit rate, meaning what fraction of the memory accesses hit the cache. So that fraction of memory accesses would have to incur only the cache latency. For the remaining fraction of memory accesses, I would have to incur the latency of memory, which is 15 cycles. So I plug all these numbers in, I get 1 cycle for the cache latency. The cache hit rate for our example is 2 hits divided by 5 total accesses, and then I have to sum it up with 3 out of 5 times I have to go to the main memory, and that takes me 15 cycles, including the time it takes to check the cache hit or miss. And so I add them all up and I get 9.4 cycles per reference. Let's take another problem and apply the similar principles and compute the average memory access time. So in this example, we also have a disk. So I would go from cache. If it's a miss, I go to memory, main memory, and then if it is a miss in main memory, I go to disk. We didn't really talk much about how main memory is architected, but that's not essential to understand how to compute AMAT for this memory hierarchy here. And just like in the previous example, I'm going to assume that the main memory latency includes the time it takes to determine cache or miss. And also the disk latency includes the time it takes to check the main memory and the cache. I'm also going to make some assumptions about a program. I'm going to assume the program has 100 memory references and the cache hit rate is 90% and that main memory hit rate is 80%. So then the average memory access time could be computed as the following. So 90% of all memory accesses hit the cache and therefore they incur only one cycle penalty. Now 10% of memory accesses have to go to main memory, so they would incur 0.1 times 100 cycles. Now of the 10%, some fraction of them would have to go to the disk, and that fraction is defined by the miss rate in main memory. So that would be, miss rate is computed as 1 minus 80%, so that would be 20%, so that's 0.2 times the time it takes to access the disk, that is 10,000. So if you compute this equation, then you get the answer. All right, so now if you think about how to reduce the average memory access time, and the reason why we want to reduce it is so that we can improve the performance of our program. We can either try and reduce the latency of the components, that is essentially to say, let me try to improve my hardware, or I can try to find ways to increase the cache hit rate. And this could be done in a couple of different ways. Maybe you as a programmer can redesign the program to exhibit better locality and therefore it will have high hit rate, or the hardware designer can come up with better replacement policies. So besides performance, we also care about the area overhead of a cache. Now, what is the area overhead? Well, we know that a cache consumes area to store data. So the area that is used to store data is useful area in the sense that you're spending the area to store the information that you actually want to access. But the area that you're spending on tag is an overhead in the sense that they don't really store data, but that is essentially a metadata that is stored to get to the actual data that you want. So you could think of the tag array as an area overhead in the cache. So now the question is, how big is this overhead? So for this example that we talked, let's say that each data is the size of a word, and let's assume that it's a 64-bit ISA. So if it's a 64-bit ISA, each address is going to be of size 64 bits. And let's assume that each address is also going to store one word or 64 bits worth of data. So each row has 64 bits of tag for storing 64 bits of data. So that's almost like 1:1 ratio. So you're paying almost the same amount of overhead for as much overhead as the data size. That's a lot. And now if you go back to the example that we had before, and if you try to compute the overhead of this architecture, it is also quite significant. So the tag was 4 bits, and we said that the data is 1 byte. And notice that you also have another overhead for the valid bit, so that's another one additional bit. Now later on when we talk about how to implement LRU, you will notice that I also need extra bits to implement the LRU policy, but we are going to ignore that for now. Now in this architecture, for each row I have 5 bits of overhead to store 8 bits of useful data. So 5:8, and that is also not a great ratio if you think about in terms of the area overhead. So the bottom line is the area overhead of the architecture that we designed is quite significant. And the question is, could we reduce that overhead? So in the next lecture, we will be seeing how for the same tag, I can increase the amount of data that I'm going to be storing here so that I can reduce the number of tags that I need per byte of data.